So what we would like to do here is we would like to be able to derive the trig form of well-known beta function. I have written down the algebraic form of beta function here, so let's begin by doing so. To start, we're going to let a new variable x represent sine squared t, and we're going to take the derivative of that. So dx is going to be 2 sine t cosine t, right? The power rule brings the 2 in front, and then the chain rule, the derivative of sine is cosine t, and of course dt. Now the limits of integration will be affected by this. When x is 0, t is going to be sine of 0 is 0, so t would be 0. And at point where x is 1, that's the domain of the beta function, by the way, from 0 to 1. Maybe I write that up here, and of course it's implied by the integral from 0 to 1. And when x is 1, we have sine of 90 degrees, right? So t must be pi over 2. That would give me a 1, sine of 90 degrees. And these become the new limits of integration for us. So I can write beta pq. Those are the parameters, by the way, of the beta distribution. It's going to be the limits of integration from 0 to pi over 2 of sine t. Let me slide this up. Of sine t to the power of 2p minus 1 times cosine t. Okay, let me see, 1 minus x. Let me actually write this. And this is going to be 1 minus sine squared t to the power of q minus 1 times 2 sine t cosine t dt. Okay, and again, I just made the substitution here that we had. Remember, x is sine squared t, so you essentially have the expression that you see here. Now, let's see. And again, I do need to put parentheses though. Oh, sorry. Hold on. Right in here, I do need to insert parentheses. P minus 1, and then of course I have 1 minus sine squared t q minus 1. That one looks good. Okay, what we can do next is we actually combine we have a sine to a power here and a sine here. We have, in a moment, we have a cosine squared, and then the cosine here. Of course, we're going to keep that cosine for substitution, maybe, or no, that's fine. Yeah, we don't need to do that. So I will combine those in just a moment. And therefore, the beta is going to be the integral from 0 to pi over 2. Now, if I combine the sine here and the sine here, first of all, that's the 2 that you see in front of the 2 sine t cosine t. So this will give me sine t to the power of, it would be 2p minus 2 in the exponent, but then because it's multiplied by sine t, you get 2p minus 1. Now in parentheses, 1 minus sine squared, that is cosine squared. So this latter factor becomes cosine squared t to the power of q minus 1 times cosine t dt. And remember, the sine here is absorbed in this one now. All right. So in the next step, I'm just going to combine the cosines now. And this is going to be the integral from 0 to pi over 2 of 2 sine t to the 2p minus 1 power times cosine t to the power of 2q minus 1 dt. And that is what the form is, the trig form that we were seeking. So here's the answer to the trig form right there. And of course, t lies between 0 and pi over 2. and that's implied by limits of integration. Okay, so let's see. So that's what we wanted to do, but what I want to do also now, give you an example on how useful this is, what we just derived. Okay, so in my example that I made up, let's say we would like to evaluate the integral from 0 to pi over 2 of sine to the 7t cosine to the 5th power of t dt. Okay, now if we do this using just ordinary calculus without using the beta function, okay, if I do this, the way to do this is you probably do integral from 0 to pi over 2. I'm going to keep sine to the 7th power of t, write cosine to the odd power as cosine to an even power times cosine t dt. And this would prepare us for a u substitution, an impending u substitution. So I'm thinking u is going to be sine t, and du is going to be, of course, cosine t dt. Correct? So that means I need to rewrite this as 0 to pi over 2. Here's sine to the 7t, cosine to the 4th. I'm going to write that as 1 minus sine squared t. So that accounts for 1 cosine squared t, and then square that. That gives you all 4 cosine t's times cos t dt. All right. Next, we're going to expand the binomial and then multiply it by sine to the 7th power. Okay. And when we do that, we're going to get integral from 0 to pi over 2 of, I'm just going to give you the expanded form times a sine to the 7th power. Okay, and that what I got is sine to the 11th power of t, negative 2 sine to the 9th power of t, plus sine to the 7th power of t. And of course, we have our cosine t dt. Okay, and at this point, if we make this u substitution, this becomes the integral from 0 to 1. And the reason is because when t is 0, sine of t is 0, so u becomes 0. And at t equal pi over 2, sine of pi over 2 is 1. So we're back to the 0, 1 domain for the integral in terms of u. And then I can simply write this as u to the 11th, negative 2u to the 9th plus u to the 7th power, and du. Okay, and this one is now integrable. We can easily integrate this using the power rule of integrals. That's u to the 12 over 12, negative 2u to the 10th over 10, and then plus u to the 8 over 8. All of that evaluated from 0 to 1. Okay, and then once you go plug in the upper limit, so the value of the integral is going to be, the upper limit gives you 1/12 minus 2/10, which is 1/5, plus 1/8. Okay, and the lower limit just gives you 0. Right, when you put 0 for the u's, you get 0. Once you combine these fractions, you're going to see that the total of these fractions, the sum of all three of them, ends up to be 1 over 120. Okay, so that's going to be the the answer to the definite integral. So no problem evaluating it, but notice we had to go through several steps to do this. Okay, so how does this relate to our beta function? Let's do the same thing using our beta function. Okay, now before I actually can use the beta function, I want to recall a relationship. I'm going to put a note here, a relationship that exists between the beta function and the gamma function. So in general, beta of PQ is going to be the same as gamma of P times gamma of Q divided by gamma of P plus Q. And of course, provided, that's if P and Q are positive integers. Okay. Oh, actually, that's not the condition, but if P and Q are positive integers, then the consequence of that is that we can write gamma of P as P minus 1 factorial. Okay, and of course, gamma of Q is Q minus 1 factorial. So again, to clarify, this relationship does not require that P and Q are integers, but if P, Q are integers, then we can write this relationship. We can rewrite them in factorial notation. Okay, so that's what I'm gonna do now. Going back to our example now, which initially was this example. Okay, we want to evaluate that integral. So the integral from 0 to pi over 2, now I can actually use the trig form, evaluate this, and equate it as a beta function. Okay. Now notice there's no 2, by the way. There is a 2 here in the beta function written in trig form. There is a 2 in the integrand, which I do not have it in my example. There's no 2 in front of the integrand. So that means what I have is half of my beta. Therefore, I'm going to write the integral from 0 to pi over 2 of what we wanted to do, of sine to 7t cosine to the 5th power of t dt as 1/2 of beta. Now P and Q here, P and Q end up being 4 and 3, and here's why. 7 is the exponent on sine that corresponds to 2p minus 1, so that p is 4. And then 5 corresponds to 2q minus 1, which means q must be 3. Right? So that's how I get beta 4, 3. Beta function, by the way, is symmetric, so beta 4, 3 is the same as beta 3, 4. Okay, so the integral is going to be 1/2. And then I'm going to use the relationship that I just boxed in. I'm going to rewrite beta function as, sorry about this. My Microsoft is acting up. And hold on. All right, I'm back. Sorry about that. So using the relationship between beta and gamma function, now I can rewrite this as 1/2 beta 4, 3, and then because those are integers, positive integers, I can write this as gamma of 4 times gamma of 3 divided by gamma of 4 plus 3 would be 7. Now in factorial notation, I can write this as 1/2 of gamma of 4, that's going to be 3 factorial. Gamma of 3 is 2 factorial divided by gamma of 7 would be 6 factorial. And you can work out the factorials. Let me just do it for you. 6, 5, 4, 3, 2, 1. 3 factorial, of course, 3, 2, 1, and 2 factorial, 2, 1. And then we can cross out some common factors from top and the bottom. The 6 here crosses out with 3 and 2. And all that remains is going to be a 1 in the numerator, right? Because all the factors are gone. You have 1 in the numerator. In the denominator, I'm multiplying 2 times 3 times 4 times 5. And that's going to be 120, which is pretty cool. We can actually use what we just learned about the trig form of beta function to simply just plug in these. Notice that we get there much faster. So of course this has its limitation. It only works with integrals that are in this form, or I should say the integrands that are a combination of sine and cosine t, pretty much in the form of the trig form that's up here. It works really good for these. So that's all I wanted to show you, and I hope you find this useful, and we have met our objective. So that will conclude this video for us.